Hi, so this is Matt York, and I am now doing the second part of the B2, I should say, for our exam 3 and transport 2. So I'm going to start off, well, actually, first of all, the problem is we're just solving the differential equations that we just made, I shouldn't say made, that we established in part 1 of B for this cooling tower. So we actually are given a set of parameters, and we're going to go and use those to actually solve the differential equations that we just made relationships with. And then after that, we're actually going to get into graphing the plots, like making plots of water temperature, air temperature, water partial pressure, and all that stuff in terms of position. So going forward, I'm just going to import some of, oh, maybe not. I'm going to import some of the variables that we're going to need in, I said variables, I meant toolboxes. I'm going to import some of the toolboxes that we're going to need in this problem because we always need numerical Python. So I'm just going to import NumPy as NP, just basic stuff there, and plotly.io to plot later in this problem, so as PyO. And then I'm going to go to a subplots generator. So from plotly.subplots, plots, I'm going to import make subplots. And then going from another toolbox we've used before, an integration toolbox from scipy.integrate. Going to use the scipy, sorry, you got me. The solve IVP, import solve IVP. Solve our initial value problem later in this problem. We're going to need to solve an initial value problem because we're going to use guesses, and when we use a guessing generator, we need to solve initial value problem function generator. And I'm now going to also go from another toolbox we've used, SciPy to optimize. That's optimization toolbox, optimize. Now I'm going to import the root function because, again, this is going to help us solve some of the unknown values when we make our guesses. So going from that, we have a lot of, let's see if that runs really quick. It's fine. Okay. We have a lot of given information in this problem. So what I'm going to do is I'm going to, what I've already done is I've already coded in a different sheet just the given information, so that way I can just copy and paste that. So I'm just gonna go ahead and copy and paste that in here right now because I don't want to waste your time just going over all of them. So I'm gonna go to this good old trusty notebook and take all of our given information. So I'm gonna go through these variables really quick. That way you know what they are. I don't want to just copy and paste and then move on. So first of all, we have our heat transfer coefficient, and then we have, I should say heat transfer coefficient there. We have just the ideal gas law coefficient, 8.314 joules per mole Kelvin. This is the relative humidity given the problem. This is the area, the cross-sectional area. This is the velocity of the air. The liquid flow rate. This is the pressure in pascals, the height of this cooling tower, the what am I talking about? Oh, the input temperature of the water. This is the input temperature of the air. These are the constants given by, oh gosh, I forget their name, but these are three constants. And we use this equation here momentarily in a second. I forget what the equation is called again. But I'm going to use that equation. This is the constants used in that equation. And then the molecular weight of water, the molecular weight of air, the density of air, the specific heat of air, specific heat of water in a gas phase, specific heat of water in a liquid phase, and the heat of vaporization. And these are obviously all the respected units. So from there, I'm actually going to move forward. We're now going to move forward and use these Antoine constants. I've finally remembered the name. I couldn't think of them. The Antoine constants and using Antoine's equation to solve for the vapor pressures at different temperatures. So we're going to input the temperatures and get vapor pressures back. So we're going to define a function. We'll call it P vape. And we're going to do the temperatures. I always forget my colons. Okay. And what we're going to do is we're going to return the Antoine's equation. So it's 10 times A minus B divided by C plus, what am I doing? Divided by C plus temperature, but it's in Celsius right now. We need it to be, or no, sorry, it's in Kelvin right now. We need it to be in Celsius for Antoine's equation. So minus 273.15. I did not do a subtraction sign, did I? And then it's going to be, make sure everyone units. I'm pretty sure pressure. Yeah, so our pressure right now is in millimeters Hg in this equation. We need it to actually be in pascals. So we're going to divide it by 760 to get to ATMs and multiply it by 101. What is it? 325, I think. Yeah, 101.325. Okay. And going forward on that, we are going to, which that worked, so that's great. We're going to actually find the, I always forget, the mass transfer coefficient. So we're going just to use the definition of equation that we have from the book, which is the heat transfer divided by the density of air multiplied by the, oh my gosh, what's this called? The, not heat capacity, it's the specific heat of air. That's what it is. Okay, cool. So we're gonna do that to find Kc. Oh, I'm gonna do a system equation. So I'm glad that works though. And then we're going to use the more fraction, like more concentration of the air going in, or not use it. We're going to try to find that, which is equal to the relative humidity multiplied by the pressure times, or not the pressure, the vapor pressure, which we just defined. So P vape, and that is multiplied by the input temperature, which we defined as TA and above, input temperature for air, not for water. Those are two different things. And on that, we're also going to have it divided by pressure to make that equation correct. And the last, nope, not P vape, just P. Okay. And then the last thing we're going to try to find right now is the flow rate of the molar flow rate of the gas here, which is the pressure times the molecular weight of air times the, divided by R, the constant, times the input temperature of air, and divided by the velocity of the air. I gotta my parentheses right here. This is all divided by the velocity. Okay. And this should all work out. Okay, cool. So the next step is we're going to start making some of these plots because we need to make it of the water temperature, the air temperature, all those things. So we're going to start making these plots. And the first thing we're going to do is we're going to make a plot with a plot that can fit all of our data in it, and that will have even like line spaces throughout. So we're going to do a plot. Yeah, we'll just call it Z plot. And actually, you know what? I want to call it Z. Yeah, whatever. Okay. Z plot. It's equal to NP1 space so let's just look at what we need to do with the line space. So it's the starting number, which we know is 0 with height here. And then our ending number, of course, is 21. But the thing is, we need to also put our variable of height in, which we define as HT. So it's 0, 20, or 0 height and then 20. Yep. And that should be good. So now that we have our plot, we're actually going to make 2 original guesses for the output temperature for air and the output molecular or molar concentration for air. So we're going to just do let's call it T. We called it what? TA in. Let's call it TA out. And that is, this is our guess for it. So TA out G1. I'm going to call it guess, like for guess 1. And that's going to be our TA in. And we can just we'll just add 5 to it for our guess. And then we're going to do, we have what? YA in. Let's do YA out. YA out is equal to, with guess 1 is equal to our YA in multiplied by, let's just do 1.1 would give us a 10% off. It'd multiply by a factor of 10% off. So that would give us a pretty good guess as well. So we're going to go with that. And then in order for this to work, we need to do solution equals none. Okay. So, I think it's because I didn't capitalize. Maybe, yeah, that's why. Okay, so going on from there, we are now going to, all right, so now I'm actually going to start making or like using these equations. Okay, I can't talk. I'm going to start actually using the differential equations to solve these numbers now. The same ones that we discovered in part 1 of this B. So we're going to actually define a function, all of those, sorry, it's storming a little out there, but I'm going to start define a function with all of these differential equations. So I'm just going to call it, since we were trying to find the rate, I'm going to call it D of the rate of the molar concentration of the gas was Y, and then we're trying to find it of the temperature of the liquid, water, and temperature of the gas. So I'm going to call it dy, TL, Tg. And then of z, of course, is our input because it's in respect to position. And then there's other variables, so I'm just going to call it x. And now I'm going to just go in order of the exact way we found the differential equations. So first I'm going to do it in molar concentration of the gas, which would just be the first one. Right. Then I'm going to go to the temperature of the liquid, which would be the second one. And last but not least, temperature of the gas, which would be the third one. So from there, I'm going to now I guess solve. Yeah, I'm gonna solve for the other things. So we're only given a couple parameters. We're not given the parameter for every single thing we're going to use in these differential equations. I mean, you saw it was many variables. So I'm actually now going to solve for all of the variables we need to use within these differential equations. So I'm going to go ahead and start off with the molar flow rate of the gas for water. Earlier we found it for air up here. We're finding it for water now. So I'm going to call it G watt, and that is the molar concentration divided by the 1 minus the molar concentration, because that's how mole fractions work, of course. And this is multiplied by the molar flow rate of the gas for the air, as we found earlier, so G air, and that's multiplied by the molecular weight of water and the molecular weight of air. Oh, we divided by the molecular weight of air. My bad. My mistakes there. So that is the molecular flow rate of gas for water. Oh, I don't know what I'm doing there. That's not right. Okay. Anyway, we'll figure that out later if that's not going well. But anyway, so then I'm going to find the molecular flow rate of the whole system, which would just be G air plus G water. I mean, that's just easy. It's just sum less G water, make it look pretty. And then I'm going to find the molecular weight of the entire system, which would encompass the molecular flow rate of the gas of the entire system divided by the molecular flow rate of the air, and that would be divided by the molecular weight of the air added to the what's it called? Okay, so if we're trying to find the molecular weight of a whole system, we need to take the molecular flow rate divided by the molar mass and the molecular weight and the of both components. Okay, does it make sense? So we're going to take the molecular flow rate of the entire system divided by the molecular flow rate of air, which is over the molecular flow rate of molecular flow rate of air over the molar mass of air. My mistakes. And then this would be added to the exact same thing, but for water. So G watt divided by M. And then that's basically just saying molecular flow rate of a component over the molar mass of the component plus the molecular weight of, or the molecular flow rate of a different component over the molar mass of that component, summed together equals the molecular flow rate over the molar mass of the system. So then you just multiply that over, and that's why you get this. Well, divide it, I should say. But yeah, so we got that. Oh my gosh, I keep doing shift enter. Not what I mean to do. But now I'm doing a video right now, by the way. Now I'm gonna find the heat capacity for the gas in the system. So I'm going to use the heat capacity of air multiplied by the molecular flow rate of air. Oh, misdid that. And I'm going to add that to the specific heat of water multiplied by the molecular flow rate of the gaseous water. And that would give us, oh wait, what am I doing? I have to divide that by, as we just did up here, this is another system of equations. It's just manipulating equations. This is divided by G instead of G on top this time. And that, oh no, not G air, just G. Okay, so this is great. So now we are going to find the molar flux, which we already did one, relation of the molar flux in part B1, if you remember that. So we are going to actually do a different one this time using the mass transfer and dividing that by the coefficient using the ideal gas law equation multiplied by the temperature of the gas. And then we're going to multiply that by the pressure and or not the pressure, the vapor pressure, and then multiply that by the temperature of the water, which would then be subtracted by the total pressure and the mole concentration of the gas in the system, or mole fraction, if you will. So going on from there, we actually want to find our, or not find, we want to input our differential equations in now that we have, okay, function, use it, which is going to assign to an array our values that we get for these differential equations. And then we also just defined all the variables that we're going to need in order to solve this equation. So now we're just going to actually put the equations in for our differential equations, which is just the negative area, negative cross-sectional area times the molecular weight times the molar flux of water divided by the molar flow rate of the gas. That was just something we already found from part B1. Like much just like that, we have the rate of the temperature of water is equal to the cross-sectional area divided by the liquid molar flow rate multiplied by the heat capacity for the water. No, specific heat for the water. I always mess that up, which is CL up there. And then multiplied by the heat transfer coefficients, which is multiplied by the difference in temperature of gas versus liquid. And that is subtracted by the heat of vaporization times the molar flux of water. Going on to the third equation, that is the temperature of the gas. Oh, sorry, I can't think. the rate of the temperature of gas, the rate that the temperature of gas is changing. We're going to eventually put that in respective position. And that is the cross-sectional area multiplied by the heat transfer coefficient divided by the molar gas, the molar flow rate of the gas, oh my gosh, multiplied by the heat capacity of the gas, multiplied by the change in temperature of the gas, change temperature of the gas versus the liquid. Again. And let's see, what else do we got here? Oh yeah, and then of course I just need to, after of course I solve my problems, or after of course I set these equations, I want to return the answers to these problems. So I'm just going to do return dy, dtg, or dtw, sorry, dtw and dtg. And then one more step I'm going to take before I go ahead and shift enter this, which I'm guessing is going to already not be right for some reason because I have an imbalance of text, but I'm going to do one more thing before I start just trying to do some fixing. Is I'm going to use exactly what we did to solve IVP in our last exam function. So it's a solve IVP, and then it requires a couple things here. So we need the function, which is this. So we're going to go ahead and just copy and paste that function. And then it's also the range. So we already did our range is 0, height 21. I'll make sure I put HT, that's what I thought I did. Okay. 21, and then past that we're going to do the, let's see, we need a method, a time span, evaluation, dense output. Okay, so we're going to do our y, so our molar fraction of the gas component when it's coming out, which I'm gonna do y. And then the temperature of the water going in, and I'm about to be done, and the temperature of the gas coming out, which I want to make sure I have all my variables still. It's been a while. Yeah, okay. And I think I actually, I don't know, actually, I think this should be right. But method, we need a method, and we're just going to call it method. And then, wait, I mean, what am I talking about? It's not just method. We need to describe our method, and my professor likes to do redo. So I'm going to go ahead and use redo, and then we need a dense output as well, based on what it's telling me up here. Dense output, and then it's false output. It's false. I played it right now. No. I want my dense output to be true. So I'm going to have it be true. Last time it was false. That's why it got me. And then after that, I'm actually going to use another function called sol. Or like it's the same function. It's sol. It's like to solve it, and I'm going to do it of what we did up here in our z plot because that's what we already created with our line correct line spacing. So I'm going to do sol z underscore plot and see what that gives us. Oh, do I need another z? I guess. Invalid syntax. Okay, well that's exactly what I thought was going to happen, as I already had an invalid syntax. dy TLTG. I don't see anything wrong. Oh. Don't want that. Fine. Z. Oh my gosh. What am I doing? I did not put colons. Semicolon. No, just colon. Okay. All right. So I'm going to go ahead and try this now. DTG. Oh, did put a nice little. What's it called? Did I do something? Trying to put a colon there. Okay, let's check the parentheses now. 1, 2, 3, 4, 5, 6 versus 1, 2, 3. Okay, well, that would be a problem. Where else am I missing? Oh, right here. Okay. Maybe now. Actually, I think what I might have done is my Y out, TWN and TG out are not defined. So maybe that's a problem. I'm going to play around with a couple of things and then come back because I don't want to waste your time while I'm trying to find these solutions. But I'm going to be right back after I find out what is wrong. Okay, so I finally figured out my error. I had a couple parentheses wrong in my solve IVP line, and I also had a comma wrong by Radu, and then past that I needed to get some indentations up here so that it was all within the function because things weren't defined, weren't calling as defined when they, should be with this function we already defined. So anyway, actually at this point, now that this works, I just ran all of it and it works. I'm actually going to define another function and put all this within it. So the reason I'm defining this function is we need to make these differential equations converge so that we can get the answers for our differential equations. So I'm going to define a function as like my con guess, my converging guess. So I'm gonna do like con guess. And then I'm going to, I want to make my life easier. I'm going to do conj. And then I'm going to, the variables I'm going to put in here, it's more variables, just like we had earlier. So I'm just going to call that x2. And then I'm going to take our y out, so our molar concentration coming out the gas, and I'm going to set that equal to x2 in the first term of the array. And I'm going to go to our gas, the temperature of the gas coming out, and I'm going to set that to the second value in the array. Okay, so then one more thing I'm going to do really quick, just so I don't have to wear this. This solve, the solution to our solve IVP. I'm just going to make that global because when you don't make things global, sometimes it gets a little bit hard to know it's within a function and not. So I'm just gonna make the solution global because if I do that, then I don't have to worry about it being within that function. So the last thing I'm gonna do is I'm going to make sure that this function is defined within I'm going to make sure this function is defined within the other function we just defined. So we had to just indentation, add an indentation. So, okay. Oh yeah. And there's actually one more thing. So if I'm going to define this function, that's great. I can define it, but I still need to return the values for our array so we can actually get the answer we're looking for. So I'm just going to do return and then the solution, which we just said equal to up here, but I'm going to get the first term in the array for the molar concentration. So that would be 0. And then I'm going to get the last term in the array for molar concentration because we want the first and last of each of them. And I'm going to subtract that by the input of the molar concentration because no, this is lowercase, which should be, I think it's, what do we define that as? I forget. YAN. That's what. Okay. So YAN, and we are going to subtract it by that because that is the starting value of the molar concentration, and we're looking for the final. So then we're also going to do the same for the temperature of the gas coming out, which would just be Sol and the third term in the array because this is the third term, or the third one. The second one would be the temperature of the liquid going out, which we already have solved for. And this would be subtracting 1 again, and minus the T, I think TG in is what I did. Let me make sure. TGN. I'm gonna go with that. If it's wrong, then I will fix it to the variable name. I'm pretty sure that's what I defined it as earlier, though. Okay, so let's see if this works. Air embellished. Oh, I did what I always do and missed a good old colon. Let's see. How about this? Okay, cool. So now we are going to use our root solver from the toolbox as we inputted earlier and from the SciPy optimized toolbox to solve this initial value problem. Okay, we already solved the initial value problem, but to find the roots of this equation and solve for our differential equations. So I'm going to root and then con G, root of our defined function above. And I'm going to do then our Y, for more concentration coming out. So YA out. And then, oh wait, actually, I thought I was supposed to be that variable. I'm pretty sure I'm supposed to. You know what? I think it's actually supposed to be. I don't think it matters. I think, yeah, this is a different. I'm defining it as something else. So I'm just gonna do YA out G as for gas, and then I'm going to do the same thing, but for our temperature of our gas. So just these are both the guesses for these variables coming out. So we're just going to do that and we're going to see what we get here. Oh, okay. So I thought I defined our out as gas. Oh, there they are. It's as G1, I believe. I think that was the problem. Oh wait, no, it's not. Give me 1 second. I'm trying to figure out what I defined it as if it was not our guess of Y and our guess of the temperature. You know what? I think it might be this. So I'm going to go ahead. Yeah, that's, oh, I don't even think I'm supposed to be doing. Okay. Yeah, that's what I defined it as. My bad. I don't know what I'm doing. So I'm gonna go ahead. I named it TA out G1 and YA out G1. YA out. I was really close, honestly, to what I had earlier, because that's how my mom works. Anyway, though, So I'm going to add this one and we should get our answer. Oh, TA. I did it as the error earlier. All right. Should be 2, but it is 1. Root 1 G Y L. There is a mismatch between the input and output shape of the function argument. G shape should be 2, but it is 1. Okay, well, that makes things interesting. Fun continues. So this is that. This is all good. I'm going to go ahead and come back really quick because this seems like it's going to be an error that's going to take me a little bit. So I will be back. Okay, so it turns out I had more than one error. I had many errors. Most of them included just naming some of my variables. I just confused myself. Instead of like TAN, I thought it was temperature of the gas in, but it's actually temperature of the air in is what I originally named it. Should have done gas, but anyway, there was a lot of mistakes. I just had a couple other ones where I would just think, okay, like the TY or MY, like for water instead of just MW or MA. I tried to make life easier earlier, and then I confused myself. So I figured out all the places I did that, and then I actually, when I I ended up deleting what I did earlier, and I just wanted to delete the answer, but I'll just do this one more time. So con underscore G. And then this would be the, let's see, I don't want to mess this up again now. YA out G1. I'm just going to copy that. To be honest, I don't want to mess it up. Any more variable names? G1, and then I have the TA out G1. And that should give us, this should be correct now. Yep, there we go. And that gives us the array, which is beautiful and looks like the correct values. And then now we're just going to go ahead and graph all 3 of these differential equations so that we can see them in respects to position. So let's go ahead and do that. But yeah, we just found out our answers for the differential equation. And now we're going to just do, let's call it graph equals make underscore subplots. All right. And then we're going to need rows. We need 3 of them. And columns, we're going to need 1. And then we're going to make a scatter plot because that's the type we need. Type plot we need, obviously, with these different values for different positions. So we're going to do scatter, and then our X is going to be Z plot, which we defined earlier as our position plot. And our Y is going to be the respective array that we're talking about. So for the first one, it's going to be the first value in the array because this is for the more concentration of or more concentration in respects to position. So this one we're going to do Oh, actually, I missed a little thing here that's going to help me. Oh my gosh, I keep doing semicolons. It's going to give us only the values that we want in the first ones. And then we're going to also just name this really quick. So name, we'll just call it Y. Well, actually, we're not going to keep Y. Because it respects, it's the rate. It's not just the more concentration, it's the rate of the more concentration. Actually, wait. Well, the graph will show the rate. So we're just going to name Y. All right. Moving on. And then we're going to do the amount of rows, or well, not the amount of rows, the row that it's going to be in, which is just going to be in row 1, and the column it's going to be in, which it's only 1 column. So definitely be 1. And we're going to actually just copy and paste this because it's very, very similar. And I don't want to type all this out again for the temperature of the water and the temperature of the gas there. So I'm going to go ahead and make this the second value in the array and name it TW. And then this would be in row 2. And besides that, we should be good to go. So I'm going to copy this one now. And again, just change the spot in the array, the name TG, and the row. So with that, we should get a nice scatter plot. Let's see. Oh, yeah. What am I doing? This is not figure. This is what I did. Last time I did this, I named it figures. So that makes sense why I would think that. Gosh, that was a really bad mistake. All right. It's graph.add, just because I made graph the name instead of figure this time. I was going off in my last exam when I tried to plot. So let's try this. Ooh, there we go. We got 3. But to be honest with you, I think let's see. I don't know if this is correct, honestly, because with the I immediately know that when looking at the more concentration, it actually is getting more negative as position goes on, which first of all, more concentration can't be negative. So we know that we did something wrong here. So I'm going to go up and try to figure out what my mistake was. So I'm going to be back because I think that I messed up a lot of things. All right, so after a lot of looking through this entire code, I realized that I was missing a parenthesis right here. So it was only taken to the exponent of a instead of the exponent of this whole equation. So I was getting values that were really off. And now when I check my values in the array, they look like they are very reasonable. And they didn't look reasonable last time, but I just really wanted to go and check this because this is where I can really tell if it's reasonable. So actually, you know what? I'm going to, well, no, it's okay. So I can tell that this is very reasonable and that this is the correct values because in our cooling tube, we are putting the water in at the top, right? And we called the top of the tube 0. We defined it as 0. So when I'm looking at this, graph, the concentration of water should be the biggest at the top, which it is. It's the highest at the top, and then it decreases exponentially to is like very low amount at the bottom, which makes sense. And then going to my temperature of the water at the top, it is going to be hot because we're putting in hot water that's going into a cooling system. And by the time it gets to the bottom of this cooling tube, it should be at a lower temperature. So that makes sense too. And then the temperature of the gas. So when we put the gas in, we're actually putting it over here at 20 because we called 0 the positioning of the tube at the top. So when we put the gas in, the temperature is getting bigger and bigger and bigger and bigger and bigger, or well, I should bigger, hotter and hotter and hotter, hotter as it's going up because it's interacting with this hot water. So the air is actually getting hotter as it goes up in the tube, which would be at 0. So as it goes down the tube, it would be decreasing. So these all make sense. And we got our final answers. And I hope you enjoyed this video. Take care. And I really enjoyed this class.